Howdy folks, welcome back to a math video that I know you've been looking forward to for the whole year. I've been on a short hiatus since last year, but you know, my views are down, so gotta put out some new content to get them back up. So I hope you guys had a great week with Mr. Stokes last week. I know you guys were starting contradictions, but we're going to put that on hold for the moment and just get right into chapter 13, which is on probability. So 13.1 and 13.2 is what we're going to do in this video. It's about experimental and theoretical probability first. Lots of vocab, outcome, event, sample space probability, experimental, theoretical, and complement. So let's get to it. Okay, so it says you find an old clock in your attic. The hour hand of the clock is broken off between 12 and 2. How many positions are possible for the hour hand? So for the hour hand, it can go anywhere between 12 and 2. Well, technically it moves like after every second, or every minute, I guess. Maybe the hour hand moves after every minute, and then the minute hand moves after every second. That would make sense. So I guess there's 60 positions between each hour. So that would be 120 positions total for 12 to 2. Okay, so 120. For a 12-hour period, how many positions are possible for the hour hand? For a 12-hour period, so that would be 12 times 60, which is 720. What is the probability that the clock stopped sometime between 12 and 2? So that would be 120. Out of our total amount, which is 720. So that would be about 16.7%. So I just did 120 divided by 720. Okay, so now talk about probability. You've done probability before. It says in the language probability, the position of the hand between 12 and 2 would be considered a favorable outcome. An outcome is a possible result of a situation or experiment. An event may be a single outcome or a group of outcomes. For the clock, the hour's hand being about halfway between 12 and 1, or about halfway between 1 and 2, are two favorable outcomes for it to stop between 12 and 2. The set of all possible outcomes is called the sample space. Probability is measured by the likelihood an event will occur. So to calculate probability, you take, it's always between 0 and 1, and you can treat it as a percentage or a decimal. But you take the number of favorable outcomes divided by the number of total outcomes. So the number you want divided by the number of total. If it is closer to 1, it's more likely. If it's exactly 1, it's certain. If it's closer to 0, it's impossible or unlikely. Okay, so it says you can use probabilities by using the results of an experiment, by reasoning mathematically. So first we're going to talk about experimental probability, which is basically calculating the probability based off the results of an experiment. So you look at the actual result, and the number of times the event occurred will go on the top of your fraction, and you're going to divide that by the number of times it is performed, the number of times the experiment is done. So if we look at this example right here, a quality control inspector samples 500 LCD monitors and finds defects in 3 of them. What is the experimental probability that a monitor selected at random will have a defect? So the number that had defects was 3 out of 500. So you can write your probability as a fraction, or you can change it to a decimal by dividing, which would give us 0.006, or you can write it as a percentage by saying 0.6%, because we moved our decimal twice. Okay. If the company manufactures 15,240 monitors in a month, how many are likely to have a defect based on the quality inspector's results? So this one you need to look at your probability, which was, what, 0.006? So we say 0.006, and we can just multiply that by the number that we're doing, which is 15,240, to give us a good estimate of how many will be defective, and that would be about 91-ish. Okay. Next, whoops. Okay, then we have theoretical probability, which is probably what you're thinking of when you actually think of probability. This is the likelihood an event will occur based on mathematical reasoning. When they refer to standard number cubes, that's just talking about a die, or a pair of them would be dice. It has 6 faces, numbered 1 to 6 on each face. No numbers used twice. So looking at this one, it says, what is the probability of rolling numbers that add to 7 when rolling 2 standard number cubes? So when you're rolling dice, the most favorable outcome would be 7 because it has the most number of combinations. So if you look at this, we can kind of set up a chart here. I don't have a lot of room, but your first dice can be 1, 2, 3, 4, 5, or 6. Second dice can be 1, 2, 3, 4, 5, or 6. Okay, and then in the middle here is going to be your sum, because this is what you're looking at, your sums. I did not leave enough space here. That's fine. It's fine. It's cool. Okay, so you can get a 2. I need, wow, a new color. You can get, wow, that's not going to work. Okay. There we go. You can get a 2 by getting a 1 and a 1. You can get a 3 by getting 1 and a 2, a 4, a 5, a 6, or a 7 by getting a 6 and a 1. And then the same thing is going to be going down like this, 2, 3, 4, 5, 6, 7. Okay, if you get a 2 and a 2, that's going to make 4. 2 and a 3 makes 5. So you kind of see the pattern, 6, 7, 8. 3, 4, 5, 6, 7, 8. So you're basically just counting up on all of these. 3 and a 3 makes 6. 4 and a 4 makes 8. 5 and a 5 makes 10. 6 and a 6 makes 12. So you can see here, your 7s are all actually in this diagonal right here. Your 6s are going to be on this diagonal, and so on. So if you count those, there are actually 6 7s, I think. 1, 2, 3, 4, 5, 6, out of a total of 36, because you're going to have 36 spaces in here. So 6 out of 36, which is the same as a 6, or about 0.167. Oops. Okay, so that'd be the probability. And again, 7 is the most likely occurrence because it has the most options. 2 and a 12 are obviously the least because you can only get those one way by getting a 1 and 1 or 6 and a 6. Okay. All right. Now, what is the probability of getting a sum of 9? So 9s would be, these would be 8s, 9s would be here. So 9s, you can either get a 6 and a 3, which is this one, 5 and a 4, a 5 and a 4, or a 6 and a 3. So there's only 4 ways out of 36 for this one. And a 2 is just this guy right here. So that's only 1 out of 36. Okay, and obviously you can change this to decimals. I'm gonna let you guys do that one. Oh, and oops, I skipped one. I missed it. 13, you actually can't get a 13 because the biggest you can get is 12. So that'd be 0. Okay, and then probability of a complement. So the complement of an event consists of all the possible outcomes in a sample space that are not part of the event. So it's basically just the opposite. So for example, if you roll a number cube, the probability of rolling less than a 3 is probably rolling less than 3, which would just be 1 or 2, or 1/3. The probability of not rolling a number less than 3 would be the complement, which would be the same as saying greater than or equal to 3. Okay, and with a complement, a probability of an event and its complement will always add up to 1 because they are just opposites of each other. So if the probability of probability of picking a number 2 is 25%, the probability of not picking 2 would be 75%. So those would add up to 1. Okay, why can I not scroll down? Okay. I'm gonna have to move some stuff, I guess. Okay, a jar contains 10 red marbles, 8 green, and 5 blue, and 6 white. What is the probability that a randomly selected marble is not green? Okay, so you could add up all the ones that are not green, or what you could do is you could say 1 minus the probability that it is green. So that'd be 1 minus 8 out of, how many is there total? 10, 18, 23, 29, is that right? 1 minus 8 out of 29, which would come out to be 72%, about 0.724. Okay, so you could do that, or you could say we add up all the ones that are not green, which is red, so 10 plus 5 plus 6, which would make 15, 21 out of 29, which should be the same, 0.724. So that is complements, theoretical, experimental probability. Now we will shift over to 13.2. All right, 13.2 is about probability distributions and frequency tables. So let's get to it. Here we have a frequency table showing the speed cars are going and the number of cars that are going that speed at a certain mile marker on Highway 66. The speed limit is 65. What is the total number of cars that pass the marker? Well, the total would just be adding up all these, so that would be 15 plus 35, so 50. So 50 total. And then, let's see, what is the probability that a car stopped at random will be traveling faster than the speed limit? So the speed limit is 65, so faster than that would we be looking at this section right here. So 13 out of 50, which is 26%. Because if you just times the top by 2 and the bottom by 2, you get 26 out of 100. Okay. All right. Relative frequency. Well, a frequency table is what we were looking at before. It's a data display that shows you how often an item appears in a category. So those are categorical. Relative frequency is the ratio of the category to the total frequency. So you're basically just changing those into decimals or percentages. So if we look at this one over here, we have a frequency table about music preferences in students. And it says, what is the relative frequency of a preference for rock music? So that would just be 10 out of the total, which is what? 10, 20, plus 20 is 40, I think. 10 out of 40, so that'd be 0.25. Okay, so relative frequency is very similar to probability. You're just taking the frequency divided by the total. You can use relative frequencies to approximate the probabilities of events. So if you look at this situation here, it says a student conducts a probability experiment by tossing 3 coins, one after the other. Using the results below, what is the probability that exactly 2 heads, so the keyword here is exactly 2 heads, will appear in the next 3 tosses? So that means it has to be 2, it can't be 2 or more. Okay, so exactly 2. So if we count how many have exactly 2, that would be this, and this, and this one. Tails, heads. Okay, so that would be, what, 7 plus 6 is 13, plus 2 is 15. Out of the total, which is, oh shoot, oops, what's happening? 15 out of, hold on, all right, 15 out of 50 is the total, so that would be 30%, or 0.3. Okay, and this 3 right here where it says next 3 tosses, that's just because they're tossing 3 coins, so that doesn't really play into our probability there. Okay, last one. Oh, and there's the dog that lives with me. He lives in my house. His name's Cosby. Last, a probability distribution shows the probability of each possible outcome. So a probability distribution can be shown in a frequency table. So I think I need more room here. Whoa. Okay, that'll work. Okay, so in a racing competition, 50 archers shot 6 arrows at each target. 3 hit no bullseyes, 5 hit 1, 7 hit 2, 7 hit 3, 11 hit 4, 10 hit 5, and 7 hit 6. What is the probability distribution for bullseyes each archer hit? Okay, so there's basically 7 options here. They can hit 0 bullseyes, and then we want the probability here, I guess. So they can hit 0, they can hit 1, we need more room here, 2, 3, okay, 4, 5, or 6. So let's pretend those are just all in one column. Okay, so how many hit no bullseyes? Well, that would be 3 out of 50. How many hit 1? That would be 5 out of 50. 7 out of 50 would be 2. Wow, I'm really running around here. 7 out of 50 again would be 3. 11 out of 50 for 4. 10 out of 50 for 5. And 7 out of 50 for 6. Okay, so that's what a probability distribution looks like. It just shows you all your possible outcomes and then the probability of each of those. So really a better representation of that might be like this. Maybe if I move some things around here. Whoa. Why does it keep doing that? No, shoot. Okay, move up here. Okay, now that I have some more room. So this would be basically your event happening and the probability of that event happening. So this is what a probability distribution really looks like. So you'd say 0, 1, 2, 3, 4, 5, 6, and then it would be something like this. Okay, so that's what it should look like. You have your event, whatever it is. In this case, you're hitting bullseyes. And then the probability of that event. Notice that all of these, if you add them together, should add up to 1, because that is 100%. Okay, so that is it for 13.1 and 13.2. So you'll have this video today, you'll work on the assignment tomorrow, you'll have another video the next day. You'll just alternate back and forth, basically, between Canvas videos and then Math Excel assignments. Canvas video, Math Excel assignments, and so on, until we come back to school and can finish our conic section unit. Okay, so I will see you all when I see you. Hope you are having great times, and don't forget to do the Canvas quiz after this. Okay, thanks, bye.